Okay. So I'll be talking in the line of epidemics. So slightly different in the sense the message assumed to be small when you do spread epidemics, so that a message can transfer from one agent to another in single contact. But this is not the case in here that I'll be talking about. The other thing is it is also different in the sense the network is dynamic as well as distributed. So before I talk about this, so many of you may not be knowing what is this IDRBT, just 2 lines. IDRBT is one of the 5 institutions that RBI in India has established, and this particular institute focuses mainly on how technology adoption occurs in banking and financial industries in India. And it works almost all the fields, almost all the fields, starting from algorithms till networks till analytics, and enforce banks to use it for their own purpose. And this is a work in collaboration with our lab members and 2 collaborators back in Kharagpur. Yeah. So I'll quickly go to the problem. So first I'll describe the problem, and then I'll describe the network and the setups, agents configuration, message configurations, and then we'll see how message can be spread when message is relatively larger. And then we'll see some analysis, mathematical models, and then we'll do have some concluding remarks. Yeah. So let us come to problem definition. So, so the network that we consider is dynamic as well as distributed, in the sense we do not consider to have a central agent who monitors the message spreading. Right? And a dynamic because the links are not activated all throughout the network lifetime. So links get activated only at particular times. A message can be passed from one agent to another only if a link is active. And it, because the network is dynamic, you cannot spread message without storing in the agents. Hence, you need epidemic style message spreading. Okay. So now, as I said, often we assume that a single contact duration or single contact opportunity is sufficient to spread a piece of information or a piece of infection. But here, what if you need multiple contact opportunities to spread a message? And with epidemic, we can say that how epidemic can be spread if an agent needs multiple contact opportunities to get infected. Okay. So the obvious solution here is, if it is a big message, then split the message into packets and try to transfer one packet in one contact opportunity. Right? And then there are several questions comes into picture. First thing is, do the epidemic spreading speed gets affected by the splitting of the message? Next, is there any impact of underlying network structure on the spreading speed? Then we know that that epidemic-like message spreading is quite costly because it takes a lot of network resource. Therefore, in this particular case where you need multiple contact opportunity to send a message, how do we control network resource usage? In other terms, how do we control the network resource wastage? Yeah. So to answer these questions, we consider simple broadcast, and we will propose some efficient algorithm which can control the wastage. So now coming to the setup. So underlying network can be represented in a graph where V nodes are the agents, and the edges from a node denotes the potential neighbors of a node. Okay, and by potential neighbors I mean you consider a network lifetime. In that lifetime, if say a set of agents can come into contact, we consider those set over a period of time are the potential neighbors, but they need not be activated at the same time step. Okay, and then what is the message configuration? Simple. We have a big message. We need to divide it into packets, and further the packets are divided grouped into a set of segments. Now, why do we group again these packets into segments? We will come to it a bit later. It has to do with the network resource usage. Yeah. So now let us look into what exactly the network dynamic and distributed network configurations we are considering here. Let us assume that these are the agents in the network, and for UI, these are the nodes, these encircled nodes, right, with whom UI can connect not at one single time step, but over a period of time. So similarly, it is there for I have drawn for this UI, but every single agent can draw his own neighbor set. And then UI, let's say at T, he can communicate with one of its neighbors, and then at T plus 1, for example, and with the other. Sorry. Yeah. Now, what is the so in terms of transfer protocols, let us define two basic terms. One is called sender and other is called non-sender. What do I mean by sender? A sender is a node who has all the packets of a message, whereby if a node has all the packets of a message, then he can send the packets to a next agent. And what is a non-sender? An agent who is having no packets or not all packets. Thereby, he cannot forward a packet to a next agent or to its neighbors. And in epidemics, basically, if you have an infection, then I try to infect others, which is basically a push technique. Now, what is pull technique? It is like I do not have a message, but I want a message from someone who has the message. So these two are different in the sense who initiates the communication and who requests the packet. And we shall see that this just simple variation who initiates the communication, it has a remarkable impact on the resource usage. Okay, so just quickly we shall go through like what the push technique is. Let's say UI has a message at say T plus 1, he sends one of its neighbors, and has some particular direction to use? Oh. Okay, so at T plus 1, it sends a message to one of its neighbors. At T plus 2, now you see that two agents are having the message, so both of them can send a message to their neighbors. However, if UI initiates the communication channel with one of the already transferred neighbor, then it is considered as a useless communication. Hence, we will consider it as a wastage of the network resource, because UI has to establish the communication line with his neighbor, but he will discover that no, they have this already has the message, so no further message transfer takes place. Hence, this establishment is wastage. Now, what is the pull technique? Here we see that those who do not have the message, they will try to find the message. So I have not drawn all the lines, the green lines, but just for example, I have shown that this is the node who establishes a communication or who requests a correct agent who has the message. But in this case, he requests an agent who has no message. Hence, this communication line is basically a resource wastage. Similarly, but in the next time step, as you can see that UI and these node become sender because they now have the message, and anybody who connects to this node, he will get the message. But again, the same thing. I have not drawn all the for all the links for all the nodes, but for example, this, if he is connecting with this node, then it is a wastage. So it is not quite difficult to see that when we use a pull technique, and at the initial stage of epidemic, the resource usage wastage would be much higher, right? However, in the earlier case, you see those who had the message, they will push to other nodes. Therefore, the resource wastage will happen, will heavily take place towards the end of the epidemic spreading. So in this, we mainly measure two metrics. One is the delay. That means source node starts spreading the packets from it, and all the nodes receive all the packets at that time. So from starting at source and all the nodes receive all the packet is the time duration called as broadcast time. We also measure TI. What is this TI? I is the number of senders present. Is the number of senders in the system, and TI is the time required to create I senders in the network, right? And then the wastage. So essentially, wastage is the useless number of useless contacts, and this quantity just says that what is the number of total number of contacts. The fraction of total number of contacts which are useless. So basically, a broadcast wastage. That's what we considered. Now let us see in presence of message splitting how these push and pull algorithms can be utilized. So we shall talk about push, which here we call as blind push. Also we consider pull. These are two basic techniques. We shall see that these two basic techniques has advantages as well as disadvantages. So we will combine that to find a efficient strategy, which is called as X% strategy. But this strategy, this X% strategy is not will not be useful for the distributed setting that we have considered in this work. Therefore, we look for a distributed version of this protocol, which is called Push-Pull-with-Giveup. So let us look at blind push, each of these protocols. In the simplest case, let's say a message has two packets, and this is the source node. At T1, he establishes a communication and transfers only one packet. So that's the initial assumption that in each contact only one packet of a message will be transferred. At T2, he establishes a communication with another neighbor and transfers another packet. And let's say at T3, now these T1, T3 are increasing in time. So now this, at T3, this agent becomes sender. However, this agent is yet to become the sender. And then at T4, because there are two senders in the system, they can simultaneously send their packets to their neighbors. Hence, you see that this is one edge which transfers the packet. This is another edge which also transfers the packet. Yeah, so that has to do with we need to restrict the resource usage. I'll tell. So let's say in this case it has one single message. Now, if he tries to communicate and he should get the message, it's true. But let us say he again establishes a connection, then he won't get the next packet. So it's just a restriction that makes sure that that's where the segment comes into play. Here it's the whole packet, but we can divide this the group.
Are there use cases where this setup is taken? I think that is the question. Are there use cases where this setup is taken?
No, I mean.
Can you tell about some use case where this setup is practical?
Okay, so
until the entire message comes, it's no point in sending that.
Yeah. So I mean, we shall see how this message segmentation has an effect in the resource usage. Network? Yeah, I mean, this is similar to network coding. Yeah. Then what you can realize that if towards the end of the epidemic spreading, if most of the agents have all the packets in the of a message, then towards the end you have more of this kind of links which will be considered as a wastage. So now let us see. So obviously the question is, how do we reduce that wastage? Then let us see the pool technique. So in pool technique, what we see then the basic pool technique, that those who do not have the packet will request other neighbors for a packet. So here, as you can see, that all those who are not having the packets, they are trying to request others. And then only this connection will get a success, others won't. But in this particular case, what we are ensuring that even if this node gets two simultaneous connections, but we ensure that only one packet gets transferred to this neighbor. It could be this neighbor also. And then again, in the next time step, another agent gets another packet, but he is not having the full all the packets in the message. Therefore, he tries to request for another packet, and it is incidental that he requests this node, because at that particular time he could establish a communication with this particular node, but it is a failure case. Then, as you can see, because most of the agents will not have the full set of packets of a message, initially it will have a lot of resource wastage because a lot of failure connections. But as you go towards the end, it's expected that less wastage should happen. Yeah. So this is the kind of results that I was making a kind of hypothesis that This is the number, so green line, solid green line, blue line is the number of total number of atoms or the connection establishment happens over time. And dotted blue line is the successful number of atoms. This pink line is in the push case. So what is evident here is initially pull case will have more of unsuccessful atoms. Push case will have more unsuccessful atoms towards the end. So now the question is, can we merge these two techniques together and take the advantage of both of them, these two techniques? This network is on a Nutella network. Nutella is one of the peer-to-peer file sharing network. We did this experiment on a snapshot of a Nutella network. So what we did is we assumed that if a network has some X% of senders already in the system, then instead of pushing the message, agents should start pulling the message. So initially, all the agents who has the message, they will push to the neighbors. Once a network has, let's say, some 50% of the agents have full of all the packets of a message, then the network, the system converts to a pool, so that towards the end we reduce the network resource wastage. Okay, but this strategy has a problem. So this X% is difficult to measure because we consider the network to be distributed. So we need some kind of distributed version of this X% strategy, right? So now we came up with this push-pull-with-give-up strategy. What does strategy do? Let us see. So each node keeps a counter, those who started pushing. So he initially source is the only node who has all the packets, and he initiates a variable failure which is equal to 0. So now let's say at T1 he establishes a connection and transfer the packet, one packet, and as soon as this node gets its first packet, he starts pulling, assuming that many other nodes in the network already became sender. And UI, at the same time, he establishes another communication with this neighbor, and in next time step, what happens? This node try to pull a message from one of the neighbor, and incidentally it is this neighbor and he is not having the message, hence it is contributing to the wastage. Now in T3, this node again start pulling, but if it establishes a communication with this node, then it is again contributing to the unsuccessful attempt, that means wastage. So now, so also at T3, another packet, the UI could transfer to this neighbor, so now this becomes a sender. However, at T4, if again UI finds a connection with this neighbor, then it is again a wastage. And that means it is a failure. I increase the counter, failure. Now let us say that this failure, so UI, the strategy is this counter, if it is greater than a threshold, then he will stop pushing and will let others to connect to him so that he can just respond to the connection, right? So here just I say for the sake of example, I said failure is 1 and threshold is if 1, then it is essentially a failure. So he will basically stop pushing. Now, let us see some analysis of these algorithms. Okay, so among the algorithms, blind push is quite simple and analytically tractable to do some kind of mathematical analysis. So, and this we do it on a complete graph topology. That essentially means every node is connected to others, and at a particular time, you pick up a random node and send a message, send a packet to that node. We also have, we'll see some results on real network, which is Nutella network. Yeah. So let us see some first the simulation results. Then I shall quickly go through how to reach to a analytical bound. So what we can see here that so this curve particularly shows the amount of time required to make all the agents have all the packets of the message, and it grows almost like linearly. Now, so these different plots shows if a packet has here m equal k equal to 2 means that a message has 2 packets and only 1 segment. That means if a node has 2 packets of the same message, then he becomes the sender. Similarly, a message has 4 packets, a message has 8 packets and 16 packets. So with the larger size of packet, the growth in the broadcast time is almost similar. And the most interesting part was this thing. So this is the time required to create the first sender. That means the source agent keep connecting with its neighbors and spreading 1 packets to each. The first time he connects to already selected neighbor, at that time next node becomes a sender. That's what is the T1. So the first node becomes a sender except the source. And so what we shall do is we'll try to figure out what is T1 in the next. Yeah. So the quick result, it look like very complicated, but it's I'll tell the steps briefly. So at T, so what happens? Second sender is getting created at T only if until T minus 1 I have selected only the nodes who has no packets in 2 packet case, right? So therefore at T I have to select one of the agents who already got selected in T minus 1 time steps. So this is exactly what the number of nodes till T minus 1, and I want to select one of them randomly, and these are like up until T minus 1 step I was selecting the nodes which were not already selected up to that time. Yeah. So this leads to like this quantity, and then expected value is of, well, I'll not go through what how we get into, but roughly the expected T1, if in the generalized case a packet has k, a message has k packets, it tends equal to like n to the power k minus 1 by k. So so this was the case on complete graph strategy, complete graph topology, but let us see on some sparse network, for example regular graph and regular trees. This result shows with the increasing node degree, T shows some interesting property here, the broadcast delay. it has a optimal, means a graph. If I keep, if I make the graph to have a certain degree, for example, regular tree or regular graph, then at a particular node degree, we see the optimal T star as well as the optimal wastage. And this is basically because, so 2-3 minutes I'll take. So this is basically because as you reduce the number of degrees, you are going to select from a limited set of neighbors. Right. Yeah. So now the same we do on real networks, and the networks, the snapshot are a bit old, but we wanted to look into some peer-to-peer networks, and they were taken on the same, snapshots are taken in the same year at different months, and this is roughly the average, the degree of the nodes. So here what we see is we perform the comparative analysis on the broadcast delay of the 3 protocols. You can easily see for any message, any number of packets in a message, the broadcast delay is minimum when we use the distributed version of X% strategy. And however, this wastage has a bit higher than X% strategy. It's because, see, push and pull are combined from the very initial time steps. So therefore, the wastage is relatively higher than X% strategy, but it is much less than the blind push. So here are the observations. The first observation is the broadcast time and wastage can be reduced if we use the push-pull-with-give-up compared to blind push. However, it has and also it is better than X% strategy, but it has relatively higher wastage. So there are some the effect on, we have seen in the real graph that the sparsity has an effect on the message spreading and the wastage. So we also did the experiment on the sparse graph by making the original data set, by removing the set of edges from the original data sets. And this is the kind of result. So I'll so we defined a new problem for information dissemination where the message is large. It's not sufficient. The content may not be sufficient to transfer a message in the duration, and we have seen that the speed of broadcast can significantly vary depending on the network structure, depending on the number of segments, and we have seen that in sparse network case there is an optimal D, that optimal degree D, that helps to reduce both the wastage, the network wastage, resource wastage, and broadcast time. Yeah. So, thank you.